In example 1 from our chapter here on stability, let's go back to one of the intuitive examples we had back in the lecture. Here we have a thin bar which is pinned to ground at O. We're going to start there on the left hand side with the bar hanging straight down from O and give it a small bump, a perturbation about that equilibrium state. So for this we'll derive our equation motion using the Newton-Euler equations, and then assuming that we're going to be looking for small motion, that is small angles of oscillations such that theta is small and sine of theta can be approximated by the angle itself. In our differential equation, this here becomes a theta. So if you transform that, take a Laplace transform of that differential equation and solve for the transformed theta, you get S times the initial value for theta plus an initial theta dot divided by S squared plus 3g over L. So that is our transformed representation of a response for theta. We know that our denominator d from this is simply S squared plus 3g over L. And to find the roots, the poles, we set that equal to a 0. And our two roots are purely imaginary. This is plus or minus j square root of 3g over L. So the point here being that our poles are purely imaginary. They are appearing in complex conjugate pairs. That's no surprise, that's always true. And so with our distinct roots, we can do our partial fraction expansion in terms of our residues A1, then divided by S minus P1, then residue A2 divided by S minus P2. But of course, since these roots are complex conjugate pairs, this is actually A1 complex conjugate divided by S minus P1, like that. And as we've done a number of times, when you add two complex numbers together that are complex conjugates of each other, you get twice the real part. And as we've done a number of times when we do our inverse Laplace transform of this, our form that we end up with, I'm not going to write down what A and B are, but we get cosine square root of 3gl all times t plus b sine 3g over lt. So this quantifies what our intuition gave us, I think, on the example when we talked about it in lecture. You give this a small bump and you get oscillations. The details of this are not given because we didn't actually evaluate numerically our residues. We don't really care about that because we're looking for the qualitative description of the response. And it's going to be small oscillations about the equilibrium state. On the other hand, if we take our same thin bar, pinned to ground here at O, but we started out near the top, just a very small perturbation away from that state, and we derive our equation of motion, this time with theta being measured from the angle there at the top, we get basically the same equation of motion with a different sign. That sign difference is just because of the line from which we measure our angle of rotation. If we are going to try to assume that the angle of rotation is small, sine theta becomes theta itself. Our denominator for a transform of variable is going to be S squared minus 3g over L. To find the roots of that, the poles, we get the two poles being P1, P2 plus or minus square root of 3G over L. Kind of looks like it did for the other case, except for the very important difference there that on the left-hand side we got a J. On this side we have two real roots. And the key thing here is that one root, one pole is positive. That is what makes all the difference in the world. Because what we have then is our transformed response, theta of S, distinct poles. We get A1 divided by S minus P1, A2 divided by S minus P2. Here the roots are not complex conjugates of each other. They're not going to produce cosines and sines. Rather what you will get is just exponentials. So it's going to be A1 E square root of 3G over L times T, and A2 will be E minus square root of 3G over LT. The second one is okay. I mean, that's going to be decaying in time. But the one that defines for us whether this is a stable response is this part here, which is growing exponentially. And that's the one that wins out in time. So again, if you start the bar in an upright state, give it a bump, it doesn't come back. It doesn't come back. It doesn't have oscillation. In our equation that we have for the response, recall that this is based on linearized equation of motion. So this is our linearized response. It breaks down when theta becomes large, or at least larger, such we can replace the sine by the angle itself. Don't be too concerned about the form. That it's actually hard to solve for what it actually is. The linearized equation does us a lot of good in knowing that if you give it a small bump, it doesn't come back. In the other state, you give it a small bump, it will oscillate back and forth with small amplitude oscillations. If there were damping in there, we could have put a viscous damper there at the pin O. You would find out that it would come back to the equilibrium state as the sines and cosines decayed away.